So the question for this problem is, how do you put the data in to run your ANOVA? And the answer is that you don't have the data that you need to put into an ANOVA analysis. The problem is not set up for that purpose. The real purpose is to teach you how decisions are made in a Tukey analysis or any post-hoc comparison of group means, and where do those decisions come from? And they come from the mean squares, which of course, if you understand how an F is made, it depends on these mean squares. And so the value of the mean squares are used to make really this one here to make with the within to make decisions about whether group differences actually exist. So first, let me just show you that if you go to StatCrunch, inside of a module, you'll see the data sets that are used, and it will give you an idea of how to set up data for various problems. What form should the data take? How are they organized? Is always an essential question in data analysis. Is how am I supposed to set these data up? And if you go into StatCrunch, you can see examples of what they did to set up their data. What data are they using? What sort of variables are listed? Here we see we have two variables or one variable brand, cold versus hot, and then here's some means probably for that. Sometimes you just have groups listed out there. Here we have probably some sort of scores by type of machine. How many participants in each group? 10. So you can always look at StatCrunch to give you an idea. It's right there in your file. Now, in this problem, it's trying to teach you the idea of how do you tell the difference between groups. Now here, we're probably going to make a decision. This F is very high. An F of about 3 is extremely high under the null hypothesis, and so an F of 8 is very high. And we're probably going to reject the null hypothesis that there is no difference between any group, which means that the mean of group 1 is the same as group 2, is the same as group 3, same as group 4. Now let's just view an example of this problem. I'm not going to show you this actual problem, but here we go. Here's the example, and it just takes you step by step through the problems. And the first thing you're going to do is compute the mean square for within groups. And we have to decide if we reject the null hypothesis. So our critical F, here it is. Our critical F is 3.95, our F is 8. We're going to reject the null hypothesis. And now the next idea is, how are we going to decide which groups are actually different from each other? So if we look at our data here, we have 4 groups. I typed this in. So, that's how you do it. I just typed it in over here to make myself a little worksheet. Let's look at our 4 group means. Look, probably if an F is significant, or the obtained F is greater than the critical F, we can see that group 4 is probably the outlier, right? It's the group that is probably not the same as the rest. We don't really know. Look, probably group 2 and group 3 are probably pretty much the same. They're probably not different from each other. Maybe group 2 is different than group 1, maybe not. Maybe group 3 is different than group 1. We don't know. But probably, look, this group 4 is probably different from group 1, probably different from group 2. But we can't tell by eyeballing, so we need to find out this critical value, which means what's the difference between groups that has to exist. Now, Now here they are computed right here. Oh, this is the actual value, and this is the critical value right here. And let's just look, we'll look at the answer first. The difference between group 1 and group 2 is 6.3, but it's not different. They're not different from each other until the difference is 11. So they're not different. Group 1 versus group 3, not different. Close. Now look, group 1 versus group 4, different. 2 is not different than 3. We knew that to begin with. 2 is different than 4, and 3 is not different than 4. And how do we tell? 7.11 is not greater than 9.19. 10.25 is greater than 9.19. So we have all the information to get us to this point. Okay? We can just fill in a table. We can set up our, here's what we know. We know all this stuff, all the way to here. And this is the stuff that we don't know. And to get this stuff, they're just going to teach you the idea that there's a table called Q that gives you some value as a multiplier. And here it is. You set up your data, you get that information, and then you do this big complicated calculation here. You put mean square within over 2 and then multiply by 1 over n plus 1 over n. And the idea is this value here is going to be the same for all the groups that have the same n's. Okay? And that's this and this. These two have the same. These two have the same. Then we're going to do another calculation for the values that have different n's. So we're going to get 2 different values for that multiplier. For that value under the radical. And we're going to multiply the value we get for these groups by 1 by a q, and then we're going to multiply the value we get for this by q. And in one case we're going to get 11.1, the other case we're going to get 9.2. Let's show how to get the q value. You can use your table in the back, or here's I like to use little calculators online. What did I do to get here? I just looked up critical values of studentized range Q. Alright, so I got this one, and then what was there? There was 4 groups, 120 degrees of freedom. Let's do it again. I put in 4, I knew 4. I knew the degrees of freedom, and then I calculated it, and 4.5, right? Let's go back and use the table. Let's see. This is for 0.05 on the top and 0.01 on the bottom. The lower your alpha, the higher the value has to be. Okay, so there's 4 treatments and 120, and at 0.01 the value is 4.5. So you can get it out of a table this way and get it out of the table. You can use an online calculator. 4.5. Again, that's 120 treatments, 4 treatments, and degree of freedom is equal to 120. Alpha, the lower range, 0.01. Okay, so we multiplied our cube 4.5 times the value we get when we got 22 in both of the n values. Gives a critical range 11.06. And then we get a smaller value when one of the n's is 58, which makes a lot of sense because the larger the groups, the more stable the data and the lower the critical range has to be. And so now we just make our comparisons. Once we find this critical range, we say, is 6.33 greater than 11.06? No. Is 9.47 greater than 11.06? No. Is 16.58 greater? Is the obtained difference between groups greater than the critical value? Yes. Is the obtained value greater? No. Is the obtained value greater? Yes. So we have two groups here, 1 versus 4 and 2 versus 4, that are actually different. 3 is not different than 4. 3 is not different than 2. 3 is not different than 1. And what does that mean? It means, yeah, of course they're different. Of course this is lower. But the difference is not more than what would be expected if they were actually equal and you randomly sampled out of them. And that's always the question. Let's just take a sample out of a group. Let's put everybody back in. Let's take another sample of 22. 40.4 for one sample and 46.7 out of the same group. Not impressive. That's a sampling error. Well, how about 1 versus 3? What if it's as low as 37.3? I got 46.8 when I first sampled from the group, and I got 37.3 when I again sampled from the group. And the answer is, you know what? It's not any different than what you would expect by random selection. Okay, but I got 46.8 for one group, and I got 30.2. Oh, you could not have sampled from the same group and gotten that. That would be very, very, very unusual. And so we're going to reject the idea that those two samples came from the same group. They came from different groups, because there's no way you can get that large a difference if they came from the same group. And that's what you're always doing in null hypothesis testing. You're asking the question, are these groups actually the same, or are they different somehow? Okay, just back to your problem. It's all you don't have a way to put these data into pH-stat from the data that you're given unless you just have a Q calculator pH-stat. Now, I don't use pH-stat. I don't have a machine that it works on in my house. I have no need for it. And I've just found that most students can figure out how to use pH-stat, and I don't really require students to use pH-stat. I don't even think it's a good idea to use pH-stat. And I would just use Excel, because that's what you would use for the rest of your career anyway, unless you're going to get serious and use Minitab or SPSS or something like that. Okay, thank you.